The greatest integer function. Welcome, everyone. Today, we are going to dive into a very specific and useful concept in algebra known as the greatest integer function. Now, before we get into the formal mathematical definitions and the complex notation you'll see in the next few slides, I want to give you a very intuitive way to think about it. In the simplest terms possible, you can think of this function as a rule that rounds down any number to the nearest integer. Whether you are dealing with positive or negative decimals, the goal is always to find the integer that is just below or equal to your starting value. Keep this idea of rounding down in your mind, as it will be our foundation as we move on to the formal definition in the next slide. Formal definition. The greatest integer function is denoted by f of x, where x is enclosed in square brackets. Formally, we describe this as a function from the set of all real numbers to the set of all real numbers, where the notation of x in square brackets represents the greatest integer that is less than or equal to x. I know that sounds a bit technical, so let's break down the logic behind that definition into two simple steps. First, imagine you have any number. Let's call it x. Your first task is to identify every single integer that is less than or equal to that number. Once you have that collection of integers, your second task is very straightforward. Simply look through that set and select the one with the maximum value, the largest one available. Now that we have a basic idea that this function essentially rounds down numbers, let's look at the formal mathematical definition so you can understand exactly how it works in a rigorous way. As we move into the next slide, I'll show you how to apply this specific logic to different types of numbers, especially when dealing with decimals and negative values, which can be a bit tricky. Conceptual breakdown. Now that we have looked at the formal definition of the greatest integer function, let's break it down into something more manageable. To evaluate the function, we can categorize any input, which we'll call x, into three different scenarios. First, let's look at scenario A, when x is a positive decimal. If you're dealing with a positive number that has a fractional part, the process is quite straightforward. You simply remove the decimal part. For example, if we take x equals 2.7, let's look at the integers that are less than or equal to 2.7. That set would include 0, 1, and 2. Out of that group, the greatest value is 2. Therefore, the greatest integer of 2.7 equals 2. Next, we have scenario B, when x is already an integer. In this case, remember that equal to part of our definition from the previous slide. If the number is already a whole number, the greatest integer less than or equal to it is just the number itself. For instance, if x equals 5, the greatest integer less than or equal to 5 is simply 5. So the greatest integer of 5 equals 5. Finally, let's move to scenario C, when x is a negative decimal. Now, I want you to pay close attention here, because this is where most students encounter difficulty. When we deal with negative numbers, rounding down actually means moving further away from 0 or moving to the left on the number line. Let's use an example. If x equals negative 1.2, let's list the integers that are less than or equal to negative 1.2. We would have negative 2, negative 3, negative 4, and so on. Looking at that list, the greatest value among them is negative 2. Thus, the greatest integer of negative 1.2 equals negative 2. Real-world analogy. Now, if the formal definitions and the mathematical scenarios we just discussed feel a bit abstract, let me give you a real-world analogy that might make it click. Think about the concept of completed years of age. Imagine a person who is 16.7 years old. Even though they are mathematically closer to 17, they haven't actually reached their 17th birthday yet. In legal or official documents, when we ask for their completed age, the answer is simply 16. We don't round up to 17. Instead, we only look at the last whole integer they have fully passed. This is exactly how the greatest integer function operates. Just like that person's age, the function ignores the fractional part and focuses on the largest whole number that has already been reached or passed. This should help you remember why, as we'll see in our next examples, we always move toward the lower integer, especially when dealing with those tricky negative numbers. Step-by-step examples. Now that we have covered the theory and the real-world analogy of age, let's put this into practice with some step-by-step examples to ensure you've mastered the logic. Let's look at example 1, where we want to evaluate the greatest integer function of 4.9. First, we identify our input, which is x equals 4.9. Next, following our formal definition, let's list the integers that are less than or equal to 4.9. We can see this set includes numbers like 2, 3, and 4. Finally, we look for the greatest value in that list, which is 4. So our result is, the greatest integer function of 4.9 equals 4. Moving on to example 2, which is a bit more challenging. We want to evaluate the greatest integer function of negative 0.5. Step 1, our input is x equals negative 0.5. Step 2, let's list the integers that are less than or equal to negative 0.5. On the number line, moving to the left, we find negative 1, negative 2, negative 3, and so on. Step 3, we pick the greatest integer from that set. Even though negative 1 is numerically smaller than 0, it is the largest value in our list. Therefore, the result is, the greatest integer function of negative 0.5 equals negative 1. Lastly, let's look at example 3, where we evaluate the greatest integer function of negative 3. First, we identify our number as x equals negative 3. Now, remember the rule for integers we discussed earlier. Since negative 3 is already an integer, the greatest integer less than or equal to negative 3 is simply negative 3 itself. So our result is, the greatest integer function of negative 3 equals negative 3. Keep these patterns in mind, because in the next slide, we are going to see how these specific values create the visual staircase pattern on a graph. Graphical representation. If we were to plot all these points, the graph of f of x equals x is known as a step function. If you look at the shape, it looks exactly like a series of stairs or steps. Let's break down how these steps are formed. For any x value in the interval starting at 0 and going up to, but not including, 1, written as x is in the interval 0 to 1, the value of f of x is simply 0. On your graph, this appears as a flat, horizontal line segment starting at x equals 0 and ending just before x equals 1. Moving to the next step, for x values in the interval starting at 1 and going up to, but not including, 2, that is, x is in the interval 1 to 2, the value of f of x jumps up to 1. This creates another horizontal line segment from x equals 1 to x equals 2. You'll notice that at every single integer, the graph jumps up to the next level, much like stepping up onto a new stair. Now, a very important detail for your sketches. Pay close attention to the endpoints of these segments. The left end of each segment is marked with a closed circle, which tells us that the integer value is included in that step. Conversely, the right end of each segment is marked with an open circle, indicating that the value is not included. Now that we understand how to calculate these values numerically, let's visualize what this looks like on a coordinate plane. Understanding this visual pattern is crucial, because as we will see in the next slide, a common mistake is forgetting that the function must always move to the integer that is less than or equal to our number, which is why those jumps always move downward in value for negative numbers. Common mistakes. First, let's talk about the confusion between standard rounding and the floor concept we've been discussing. When you first learn about rounding in primary school, you're taught to look for the nearest integer. So, a beginner might look at negative 1.2 and think, well, negative 1 is much closer to negative 1.2 than negative 2 is, so the answer should be negative 1. But remember our formal definition from earlier. We aren't looking for the nearest integer. We are looking for the greatest integer that is less than or equal to our number. If we look at the number line, negative 2 is less than negative 1.2, while negative 1 is actually greater than it. Therefore, the correct value must be negative 2. Always keep your eyes on the left side of the number line. Second, watch out for how you handle negative integers. I've seen many students mistakenly subtract 1 from a negative integer, for example, thinking that the greatest integer of -3 would be -4. Don't fall into that trap. As we discussed in our breakdown of scenario B, if the number is already an integer, the equal to part of our definition takes over. Since -3 is already an integer, the greatest integer less than or equal to -3 is simply -3 itself. Now, before we wrap up, I want to pause and address some common pitfalls. Even students who understand the definition often stumble on these two specific areas. If you can avoid these two mistakes, you've mastered the core logic of the function. Key takeaways. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways to ensure everything we've covered is clear. First, let's revisit the core definition. The greatest integer function, which we write as f of x equals the quantity x in square brackets, simply returns the largest integer, let's call it n, such that n is less than or equal to x. This is the fundamental rule we've been using throughout our examples. Next, let's remember our shortcuts for different types of numbers. For positive decimals, as we saw with our example of 2.7, the function effectively just removes the decimal part, leaving you with the whole number. However, be very careful with negative decimals. As we discussed during our breakdown of scenario C, for negative numbers, the function moves to the next lower integer, which means moving further to the left on the number line. So, instead of moving towards 0, you are moving away from it. Now, don't let the negative numbers trip you up when you encounter a pure integer. As we noted in our third example, for any integer z, the value of the function is simply z itself. If the number is already an integer, no change is needed. Finally, let's keep the visual aspect in mind. When you look at the graph of this function, you'll see it consists of a series of horizontal segments. Because of this specific shape, we call it a step function. If you can keep these points in mind, you'll have a solid grasp of the greatest integer function. Great job today!